Okay. So starting with the history of periodic table, in case you guys ever get a chance, there is an online article on the history. There's so many articles on the history of periodic tables. Okay. Um, so this is like Rutherford's periodic table taken from a museum. This is the book that he wrote, and this is like the periodic table that he had. So you guys already had this in grade 10, but again, just to set context on this, so this is like the timeline of the periodic table. Okay. So first, this is a good one. Yeah, 1789 is when Antoine Lavoisier, so he's a popular name in chemistry, like he's isolated a lot of elements. So yeah, he's known as father of modern chemistry. So he published a list of 33 elements or simple substances, like basic fundamental substances. That's where the word element comes from. Okay, so he's the one who first isolated oxygen as an element, for example. So he isolated a lot of individual chemical elements, and based on his findings, then John Dalton got an idea that, oh, like the things around us, they are made of tiny atoms, and then you have all these laws of chemical combinations, law of simple proportion, definite proportion, all of this stuff. Okay, then once like people could identify that there was a list of 33 elements, Dobriner, he was trying to find patterns in these elements, some similarities, differences, and he came up with Dobriner's triads. Do you guys remember Dobriner's triads?
I don't remember them.
Equal to the middle one.
Yes, Kaveri remembers, she got it. So triads, sets of 3 elements. Then if you compare.
Oh wait, yeah, then the average one, right? Was it that one?
Yes.
All right.
Yeah, and look at, like, pay attention to the year. So all of this was in early 1800s. Everything that you learned in structure of atom didn't happen till like early 1900s. So people did not have the concept of atomic number yet. People didn't know that things were made up of electrons, protons, neutrons. No one knew what the structure of atom was. They just knew that they were made up of different elements. Elements had atoms. That's it. No one knew any other details about atoms beyond like how they reacted. Yeah. So they only had atomic mass to work with, like elemental mass, and Dobriner formed patterns based on the mass. Then 1862 to 67, okay, like different, as more elements started getting, discovered, obviously Dobriner's triads did not hold through. He had his own, like drawbacks. And then you had Newland's law of octaves, and a lot of these other mid-level things happened. And by the time we got to 1869, from 33 elements, people could now recognize almost like 60 something elements, 50, 60 elements. So Mendeleev took this whole set of 60 elements. Now each of these elements had their own information, like how they reacted, what their atomic mass was, what the symbol was, who they reacted with, who they did not react with. Obviously, as the list grew, it was difficult to remember the properties of all of them. So Mendeleev was the first one to properly figure out a pattern and categorize them. Okay. So you had Mendeleev's early versions of the periodic table. Do you guys remember Mendeleev's periodic table? At least some random details about it? What the...
I actually don't remember anything. I just forgot about 10th.
Wow, okay.
63 cards and then something like that. And it was based on atomic mass.
That is absolutely right. So Mendeleev was the first person, okay, not the very first person, because Newland already had this idea, but he was the first person to put in serious thought and effort behind the repeating, like periodic properties. So do you guys remember the statement? The physical and chemical properties of elements are periodic.
Repeated after uh, like 8 elements or something like that, right?
Yes. So Newland's law of octaves, he put a number to it that okay, after every 8 elements they're repeating, which was true till like for the first 20, because they were all simple elements. But then you got the D block, which disturbed the whole thing again, and then the properties were not repeating after every 8. But there was still repetition of properties, which Mendeleev studied, and he made up his own version of the periodic table. Okay, so this is his periodic table. He based it off of mass, which was the only known information about elements at that point of time. The physical chemical properties, he based it off of what kind of compounds they formed. Like if they formed compounds of the form R2O, like you have H2O, Na2O, then he put them all in like one column. If it is RO, like MgO, CaO, he put them in the other column. And that is kind of how he formed it. Another thing I want you guys to notice is, yeah, he made up 8 groups. Each group again had subgroups, like you had A and B, like different columns. Can you guys find out a pattern, like what is the difference between A and B? Can you observe what is the difference between group A elements and group B elements? And what all elements are falling under group A and what all elements are falling under group B?
One is that A is the atomic mass is more for B than A.
Yes. Also look at this, like first example of it that we find, group A consists of lithium, sodium, potassium. Group B consists of copper, silver, gold. So Mendeleev studied these things so deeply that he recognized that there was a similarity between, say, potassium and copper or rubidium and silver, that they showed valency of 1. Like copper had valency of +1, zinc had valency of +2. But there was still a difference between copper and potassium. Like copper, silver do have tendency to show variable valencies, like it shows +1 and +2. Potassium, rubidium, all of these are highly reactive, but copper, silver, gold are not reactive at all. So he dealt with this kind of situation where there were some similarities, but a lot of differences also, by dividing them into group A and group B. So later on,
Ma'am,
yeah.
but as you said, there were variable valency or whatever charge. But
Mhm.
they, as you said, this time they did not know about electrons, right? So he could not have thought about this point.
So where he found out that was not from the electronic configuration, it was purely by observation. Like people didn't know how they reacted, but they still knew that they could still figure out the formula of water was H2O and carbon is, like carbon dioxide was CO2, like based on the mass percentages that these compounds had. Okay. So people knew of elements and compounds, like that's what Dalton said, right? That compounds are formed when atoms of elements reacted in fixed ratios of small numbers. Like they knew of the fact, they did not know the reason behind it. So the reason became clear once electrons, protons, all of these were discovered. Okay. So he could observe that copper formed CuO and Cu2O. So based on that, he could figure out the chemical properties of how it was reacting with oxygen. And just based on pure observation, right? Like if you put sodium, there's explosion, but if you put copper, there's no explosion. Like one is more reactive than the other. Like that much information they had. The reason behind why were they reacting that way? Like what was the reason that potassium could form only single valency, but others could form variable valency? The why behind it, they did not know. Okay. So yeah, Mendeleev, yes, he Siberian by birth. He worked in Russia, published first of his many periodic tables, and predicted. So this was the big thing about Mendeleev's periodic table. One, it was a reliable categorization for all these elements, and two, it was so correct that he was able to predict the existence of new elements. So earlier efforts did not take into consideration that, oh, there may be elements that we have not discovered. But Mendeleev, what he did was, oh, titanium is not fitting with aluminium, it is fitting better with like carbon, silicon, and all this. Then I'm going to leave a gap here and put titanium along with the rest of the things. And then he thought, okay, why is there a gap here? That means there must be another element over here which has similar properties as boron, aluminium, and all. Okay. So that's how he was able to predict the existence of new elements. And based on the patterns that are there, like sodium was 23, magnesium would have been, oh, this must be a print mistake. Magnesium is 24, aluminium is 27. Okay, all of these are there. Like potassium is 39, calcium is 40, titanium is 47. Matlab, this missing element ka atomic number should be somewhere between 40 and 47 or 48. So doing those kind of calculations, he was also able to predict the elements, existence of elements, along with the approximate properties. Unka atomic mass kya hoga, what sort of compounds will they form with oxygen, with hydrogen, all of that stuff. Okay, so that is the reason why Mendeleev is considered like the father of the periodic table, because his efforts were the most reliable of all. He put in the proper thing. And imagine this was in 1869. So this was before, the concept of the structure of atom, the fact that there was an electronic configuration, valency, like before all of this was formed. Okay, so that's what they were using. Then 1895 to 97, X-rays, radioactivity, electron, then discovery of all of this happened. Then coming to 1913, 1914, this was when Niels Bohr was able to propose his structure of atom. Now, at this time, like as Niels Bohr was working on the exact structure of atom, there was another person, Henry Moseley. So between 1913 and 1914, Henry Moseley experimentally established that elements are more accurately ordered according to an ordinal number. So he was the first one to give the idea of the atomic number. And then he was the one who figured out that the properties were periodic function of atomic mass, sure, but the more accurate representation is the atomic number. Okay. So he had given a relation also. So what Moseley did was he, what do you call it? So he plotted a graph of root nu versus z. So nu is basically the frequency of the X-rays emitted in the X-ray spectra of elements. And Z is of course the atomic number. Okay. So Moseley was also a physicist. So all of them were independently working on like different things. What Moseley did was, do you guys remember what the atomic spectra are? how spectrum of elements is formed?
No.
What?
I
Guys,
mean, do you mean like frequency and wavelength? How with that, how the spectrum is made, or what do you mean by how?
forget about all this. We have studied about spectrum, right?
Last chapter, what we did.
Yeah.
Yeah, ultraviolet and all that. Yeah.
So how do you get a spectrum? What do you remember of it?
Multiple frequencies come together.
Come together?
Yeah, like I don't know how to say it. Like I understand what it is, but I can't explain it, you know.
How do you produce a spectrum? Let's start with that.
Scattering of light.
Close. It's not exactly scattering. You just pass light through an element and it absorbs some frequencies and it gets excited. And then you take this and then whatever light it emits, make it pass through a prism or a like a diffraction grating or something, and record it on a screen. So what do you expect to see on the screen?
A band of colors.
Nice. So if it is pure light, you get a continuous band of colors. But if you were passing it through an element, like an excited, if you were recording an emission spectrum, then you get like certain bright lines at certain wavelengths, right? So this spectra, if you happen to do it with X-ray, like if you happen to record the X-ray spectrum, so mostly this is exactly what he did. He took the X-ray spectra for different elements, and then he calculated the frequency of the X-rays that are emitted from the element. So basically, whatever bright bands you happen to get here in the spectrum, um, in the X-ray range, he calculated, okay, what is the frequencies of the X-rays that are emitted in the spectrum. He took root of that frequency and plotted it against the atomic number of that element. Okay. So when he did that, mostly found that the graph happened to be a straight line. It was like a direct correlation between the atomic number and the frequency. So based,
Versus
hmm?
like root new versus Z means.
So whenever you're talking about graphs, right, like one quantity is plotted.
Like our distance time graphs, right?
Correct.
So like distance versus time.
Yes.
Okay.
Okay. So, based on these calculations, there's a formula also, which is not important, like you're not expected to remember. But yeah, so based on like all of his calculations, he proposed, he found out, he told everyone, like the scientific world, that atomic number Z is a more fundamental property than atomic mass. It's more important. It is what controls the whole behavior of elements. So this is what Moseley found out. So because atomic number happened to be more fundamental, a more important property than the other properties, Moseley created his periodic table based on the atomic number of elements, which we now know as the modern periodic table.
The graph was linear, so what?
So the graph was linear, which showed like a direct correlation between both. Um, Again, there's like details behind it. If you want to know, I can go deeper into it, but I can find out, I can send the sources. But the main point is that based on Moseley's experiments, he found out that atomic number is a more fundamental, a more important property than atomic mass. And that is why he created a periodic table based on the atomic number. Which, knowing all that we know right now is true. Because what is the atomic number?
Number of protons.
Correct. So atomic number is the number of protons, which in turn affects. So atomic number is the number of protons, which is equal to, what is equal to the number of protons?
Electrons.
Number of electrons. And what is the importance of the number of electrons? Like, what do the electrons decide?
The charge.
Charge?
I mean, if it's giving away or even if you're taking it. Okay, a valency is more appropriate.
Correct. Yes. So the number of electrons decides the electronic configuration, which in turn decides the valency of the element. And why is valency of the element important?
To find its
You can decide if it will take or give electron.
That is one of the things. But yeah, valency is important because depending on the valency, it will decide how an element reacts, like how reactive it is, and what all other elements will it react with, what all elements will it not react with. And thirdly, what kind of compounds will it form? Like, does it form, like, will the formula be M2O, MO2, MO? Is it going to be ionic or covalent? Like the whole property of the element, like chemical property of the element, is decided by this thing. Okay, so if you look at this chain of events, you can prove that atomic number Z is basically the most important property of an element. Like if you know the atomic number, you can predict the whole nature of the element itself. Is it going to be a metal or a non-metal? Because once you know the electronic configuration, you can figure out, will it have a tendency to give electrons or take electrons? So based on that, you can figure out if it's a metal or a non-metal, whether it's going to be electronegative or electropositive, and also to what extent. So based on the ease of giving electrons or taking electrons, you can predict how reactive it's going to be. And depending on the number of electrons, you can figure out what sort of compounds, like what sort of oxides or halides or hydroxides it's going to form. Okay. So that is the reason we are still using Moseley's periodic table, also called the modern periodic table. And it is reliable. Again, it works because Moseley takes atomic number to be the more fundamental property. Okay, now, like, this is how you get your periodic table. Some common properties of the periodic table, like what all do you observe? What does the periodic table look like?
made of different blocks.
That is correct. So it is.
Looks like actual timetable in
Yes.
our school.
Yes, you have. Does your timetable look like this? Do you have like a huge hole at
I
the?
mean, there is no hole, but I mean, it's after all periods, groups
Correct.
close to the timetable.
Correct. It is a literal table, which means that it's got horizontal rows and vertical columns. What's a special word given to horizontal rows in a periodic table?
Periods.
Correct. The horizontal rows are periods, and the vertical columns are called
Groups.
groups. How many groups, how many periods does it have?
7 periods and 18 groups.
Yes, you can see 7 horizontal rows. So you've got 7 and 18 vertical columns. Those are 18 groups. Here. What is the significance of the periods and the groups? So if you observe, again, all the elements are laid out based on the atomic number. You start with 1, 2, then 3, 4, 5, 6, 7. Like they're all in a continuous line, continuous row. Here. What else do we need?
Ma'am, could you zoom in a bit?
Sure. Let me figure out how to zoom in. Actually, is this clearer?
Yeah, this is
Yes.
This is better, right? Okay. All right. So we have, yes, 7 periods and 18 vertical groups. Now, what is the importance of the periods and the groups?
the periods decide the number of shells.
That is correct. So each period tells you how many does the element have. And
Also, both the period and groups decide the metallic or non-metallic character. You could just guess it by just seeing it.
that is correct. The whole position of it, you can figure out the metallic, non-metallic character. What does a group tell you?
The valency.
Valency, in a way, yes. More than that, it tells you how many valence electrons it has.
Yeah.
Okay.
Also, ma'am, we say like period means number of shells, but when we talk about quantum model, won't it be like different?
So, what does shell represent? Like the quantum model, you have N, L, M, right? Which of these three numbers does the number of shells represent?
N.
Yes. So, the period,
And
the highest N value that is present in that element.
So if it's 3s or whatever, so it will be in the third period.
Correct. So if the valence electron goes into 3s, then it will be in the third period. If the valence electron happens to go into like 5p, then if this is like the last electron ka this thing, then you'll find it in the 5th period. That way.
So in the period that is the N,
Hmm.
and the SPDF, that will be the block.
Correct. So again, valence electron, if it goes into 5p, then you'll find it in p block. So groups, periods, okay, right now we're discussing groups and periods. Periods give you
ma'am,
the number of shells, groups give you the number of valence electrons that it has. Yeah.
I have a doubt. So, like in the table above it, in the periods section, like where it's written periods,
Yeah.
so it says lanthanides and actinides also. So, like, are those also periods?
Yeah, because, okay, so lanthanides, let me highlight it. So the highlighted parts are lanthanides. They're called lanthanides because they follow the element lanthanum. And if you want to figure out which period it's in, it's basically whatever period lanthanum is in, they are essentially in the same period as that.
Is there like
And
a
same with the actinides.
Same with actinides, yes.
is there like a reason because of which they are different, they place differently?
Absolutely. Can you identify which block these elements belong to, lanthanides and actinides?
F block.
That is correct. So their valence electron is going into the F orbital. So that is the reason their, what do you call it, properties, like the way they react, the way they exist, it will be completely different from the other elements, which is why they need to have a block of their own.
Okay.
Yeah.
Ma'am,
Very
I had
yeah. Yeah, Rishabh?
So I had a doubt in maybe not here, but it will be used. So electronic configuration. So if we take about the D block, so
Yeah.
in that I have seen in most of the periodic table that since it's D, the outermost orbital should be D, but they sometimes even add S. So even if D is not filled, so that is because to make it more stable, or why is it like that? Because if it is D block, then the outermost orbital should be D, right? So but I have seen, so as I was saying, it's sometimes also D and S, most of them. Why is that? To make it more stable?
Actually, nahin. All of them will be D and S. Like for example, I'm picking one at random. Oh god, this is gonna reload. Please don't. Huh. Rhodium. You can see that the electronic configuration is 4d6 and 5s1. So 5s, because uska like the value of n is 5, so obviously that's going to be outside of 4, like n equal to 4. Like the shells are all arranged n equal to 1, 2, 3, 4, 5, 6, let's say, right? But when you're filling up the orbitals, the orbital with lower energy is filled up first. So basically 5s is filled up first, which is why you have strontium with 5s2. And then you start filling up the like 4d orbital. So we're not talking about the outermost electron, we're talking about the last electron that is filled. So pehle electron goes into 5s first, and then it goes into 4d. So the last electron, which orbital it goes in, is d orbital. That is why it belongs to the d block.
Then why not? Can you just show it again? Yeah. So why not it's 5s2 and then 45? Then S would be completely filled, right?
Yeah, that
Mm.
actually does make sense. S is filled, and then this also will be like half filled. But sometimes, again, each element, again, like the way the size of the element, how much of an effect the nucleus has on it, like there's different things that comes into play, which is why you end up having exceptions.
So it's like chromium and all that.
Yeah. So with chromium, it's a very obvious explanation that 3d5 is more stable, half filled is more stable. इसलिए 1s electron is like, I want to, like, let's have a half filled thing rather than an incomplete thing, which is why it's jumping into 3d5. But with rhodium, I do not know what the reason is. I'll have to look into it. I'll have to do the research on why it has an anomalous configuration. And
Ma'am,
it's rhodium, like a lot of the higher elements show this kind of anomalies. The lower elements is pretty straightforward, but as the as you keep going, like the anomalies start getting weirder.
ma'am.
Yeah.
So 5s, it's lower energy level than. Could you go back to rhodium? So 5s has a lower energy level than 4d,
Yeah.
but it's still valence orbital.
Yeah, because 5s is the outermost one. So if you lose an electron, 5s electron will be lost first, and then it'll start using the 4d electron. But when you're filling it up, you fill up the 5s first, and then you fill up the 4d.
The filling up happens due to energy level, but it's valid. That is 5s is the outermost because of the principal quantum number, because that's bigger.
Correct. So n equal to 5 is outer. Uske andar n equal to 4, and like all the others are there. So, yeah. Cool. So these are like the basics. So this whole chapter will be based on studying the periodic table. So we'll talk about the relation between electronic configuration and the periodic table. Like, if you know the position in the periodic table, can you get the electronic configuration from that? Or the other way around, if you know the electronic configuration, can you find out where it is in the periodic table? Both ways. Then we have the periodic trends. Like we'll take each block at a time, discuss like the main properties, what kind of elements you find there, and and then along with that you take it property wise also, like ionization and energy, electron gain enthalpy, electronegativity, like left to right, top to down, how it changes. Before we get into the periodic table, you guys have something about nomenclature of elements with atomic number greater than 100. Okay, so like the story of elements, like it started in like 1800s when Lavoisier identified 33 elements, and then people started isolating and discovering each individual element. That has still not stopped. We are continuously, like just mashing two atoms together and finding out what element will be formed. So in fact, all the elements beyond uranium, so most of these elements with atomic number greater than 100, like in fact 94, 95, like these all elements, two important points about them. One is that they are extremely unstable. Like in fact, uranium, I think, like uranium already shows radioactivity, and every single element after uranium, it is extremely unstable. They have short half lives, which means that the nucleus is so loaded, there's a lot of protons and neutrons that they cannot stay together, like they break apart. So when this happens, we say that that atomic, like that atom has decayed. So that's what happens in fission, and that's what happens in atom bombs. You forcefully decay, and that is accompanied by a lot of energy release. That's how atomic bombs work. Uh, and that's how your nuclear reactors work. So when this decay happens, you harness that energy and convert it into electric energy.
Ma'am, do atoms decay like naturally also?
Yeah. So in fact, all the elements beyond uranium decay naturally. So they have short half-life, they're unstable, and also a lot of them are synthetically produced. So they're produced in the laboratories like CERN, uh, all these facilities, where they just mash two bigger atoms together and hope that they stick together and form like a really big element.
Ma'am,
Yeah.
for like an atom bomb or something, how many atoms of the radioactive element would you need for it to be like exploding in a really big magnitude?
At least one. Even if you have like one single atom, okay, then like if you want the effects of a bomb, you need to have quite a bit. But again, I'm not well versed with these calculations. But even if you have, in terms of milligrams, right, like a tiny tablet, even that quantity is enough to set apart like a large explosion. Individual atoms in single digits, no, I don't think it's going to affect so much. But even if you have like a million atoms, that will affect, release a lot of.
Ma'am, I doubt a lot of people are well versed with knowing how to make an atom bomb.
Whoever was, I think they passed away. They were alive during the 1940s, and now I don't.
For the better.
Yeah, hopefully.
Ma'am,
Yeah.
if they decay naturally,
Mm.
so in mines and all that, where they are actually excavated from, those places would be at really high risk, right?
They are, yeah. Which is why, a place like Chernobyl, which had that huge nuclear reactor explosion, it's closed off. It's not open to public. Even if you want to go, you need to like wear a protective suit and then carry instrument to tell you where radioactivity is high versus low, where it is safe to go versus not safe to go. Absolutely.
But like naturally decaying like elements are made in laboratories, no?
Not all of them. Like uranium, I think thorium, where is thorium? H.
Uh,
Fine.
thorium is there 90?
Oh, thorium is before uranium. Yeah. So these do show like radioactive properties. Uh, uranium is considered to be the last naturally occurring element. So everything after this is considered as synthetic.
Oh, why? What is the use of actually making them if they're not naturally available? Like, what is the use of them?
So some elements are really useful, like you use tiny quantities of these elements because of their radioactivity. I don't remember. I think it's Americium. I don't know how it's pronounced. Either this or Californium. Like one of these two is used in smoke alarms. Um, a lot of like a couple of them would be used in like batteries, the way you have lithium ion batteries, like the decay, the radioactive decay itself, you harness that energy and you save that energy. But yeah, use it in like really, really tiny quantities, like in terms of milligrams, not even a few grams, 1 gram, 2 grams, something like that. And a lot,
Are all radioactive?
sorry, what?
Are all of these radioactive?
Yes, all of them are, they're unstable. So the radioactivity, the extent of it varies. Some of them are stable for a larger amount of time. The really higher ones like livermorium, francium, these all decay in a matter of seconds. Like francium was, we don't know enough information about it, in fact, because it decays like really, really fast. Some of them stay there for a few seconds. Some of them take a long time to decompose. It takes like their half life is in the range of hours, maybe. So the extent of it changes, but they're all naturally radioactive. Yes.
I had one more doubt. I forgot why were elements after 57 kept in a different part? Were they very reactive or something? I just forgot the reason.
After 57, not all of them after 57.
Okay, whatever is kept over there, the F block,
Yeah,
why were they kept there for a highly reactive purpose, or what was the reason?
They have similar properties to lanthanum, no?
lanthanum. Yeah,
Lanthanum, sorry. Same with the AC element. I don't know its name.
actinium.
Actinium, yeah.
Yeah, so lanthanum. Oh, keep accidentally clicking on it. Lanthanum and actinium. So point one, the answer was in the question itself, Rishit. So this is called F block because their valence electron goes in the F subshell. You can see it starts with 4f1, 4f3, 4f4, 4f5, 4f6. So it goes in the F orbital, which makes its properties very different from rest of the D block elements, obviously, the way S block is different from B block. And second, they are called lanthanides and they're kept behind lanthanum because all their properties are very, very, very similar to lanthanum. Same with actinium. Again, so this lanthanum, the 4F is filled. Actinides, the 5F is filled. But again, like both of these rows are F block elements. And yeah, just like how S block elements are different from P block, different from B block, they have completely different properties. And they're very similar to the first member, like they're very similar to lanthanum and actinium. That's why they're called lanthanides and actinides.
Ma'am,
Hmm?
do lanthanides and actinides like have similar properties to each other?
Close enough, yes. Roughly, yes. If you look at the finer details, the differences will arise. But yeah, overall, they would have similar properties. Mm,
Ma'am, when you like select a random element, there is a picture. So what does that mean? Like, is it because of that country or something like that, or is it just the meaning of the element or something like that?
I don't actually know what element they have. Yeah, I think it's just a visual association of that element. Like nihonium is named after the country Japan. So you have like a Japanese flag and Japanese characters there. Uh, Copernicium is named after Copernicus. Do any of you know who Copernicus is?
I've heard the name, but I don't know where.
He was one of the first persons to propose that the sun is the center of solar system and not the earth. So this was way back in like 1600s. And obviously everyone thought they were the center of universe. So they were like, earth is at the center, everything else revolved around the earth. But Copernicus was the first person, like based on scientific calculations and observation of how the planets and like how the stars, how the sun moved. He said that no, Earth is not the center of the solar system, much less the universe. The sun is the center of the solar system, and the planets revolve around it.
Ma'am,
Yeah.
if a new element is discovered,
Hmm.
then it's not obvious that it's going to be put right. Like suppose after whatever the 118th element is, something is discovered.
Hmm.
So will it be by default put in the first group?
It depends on like so
On
what
the properties it has.
correct. So what people do is people study it. If you're able to get the atomic number, well and good. If the atomic number happens to be 120, you know that 119 is going to go here. So this will be the place for it, 120 kDa. Or you study, like you try to get whatever properties that you can. Like you study its spectrum, you study, if you have it long enough to react, you study its reactions. Or theoretically you're like, okay, we were able to make this element by combining these two atoms and these were the side products, so I suppose this element would have so and so atomic number, so and so mass number. So yeah, you study it first and based on the properties you give it a place.
If it's not artificial, if it's a natural element,
Hmm. Still you study it, you see how it, like one, you figure out its atomic mass, atomic number based on spectroscopic studies. You see how it would react, like what state you found it in. So this is what research consists of. Like
so there's a chance if it could like fit into any one of the groups, right? So adding that element to the table, would it cause a disturbance in other elements?
no, all of the other elements are just fit in their places. Like all these atomic numbers have been discovered, verified, set. If you discover a new element, it's going to be beyond 118, as you said. So you will create a new row or a new column or both and give it a place there.
Hmm.
Okay.
So, ma'am, I had one more doubt about electronic configuration. So, for example, if the prince,
Come back to it later because I just outlined the whole chapter, right? So I told you we'll be discussing electronic configuration later on. Okay.
okay,
So, Kaveri, you brought up a really good point that, if and when a new element is discovered, yes, the place, like all these elements have their places, they're all set here. And you would create a new place because it is always definitely going to be beyond 180. Now, how would you refer to this new element? What name would you give it so that everybody recognizes it?
That table.
Yes, that is correct. Do you guys remember our friends IUPAC?
International Union of Pure and Applied Chemistry.
That is correct. Where have you come across IUPAC before?
They're the people who name elements, right?
Yes,
I think.
yes. Not just elements, like, yeah, they're the ones who decide units and like things related to chemistry. You have come across IUPAC in grade 10. That's what I'm getting at.
And carbon compounds.
That is correct. Sanat, Rishit, what about you guys? Do you remember?
I just
Yes,
forgot the
ma'am.
chapter name, but I do remember that.
Yeah, like carbon compounds, organic chemistry. Organic compounds जो है, there's a set, like you just can't keep creating independent names like forever. It'll be difficult to remember all of them, right? So IUPAC defines like, follow this logic, then everybody all over the world can know what compound it represents without any confusion. So that's the job of IUPAC, set standards so that people are not fighting. So they do the same thing with these like names for new elements as well. If you observe the periodic table, what do you notice about their names? Like, for example, you have europium.
It has a suffix of IUM.
Yes. What else? You have curium. You have berkelium. You have fermium. Who else?
Ma'am, what is the question again?
Like, I just want you guys to observe names of elements and see like if you're able to get some pattern out of it, or just general observation. What do you guys think about it?
Most of them have em in the end.
That is one observation, yes.
Some of them are just straight up planet names.
Planet
Plutonium.
Uranus,
A
Uranium.
lot of them are named after like either countries or people like scientists.
Very nice. Correct. So you have Einsteinium to honor Einstein, Fermium to honor Fermi. Fermi is another scientist, philosopher.
But when there is some scientist name, it does not mean they discovered it, right? It's just to honor them. Or they do have something to do with discovering it.
I think it's
Oh,
just to honor them.
yeah, like sometimes it's given just to honor them, like past Nobel winners. But sometimes, like especially you see this in olden days, that yeah, if a scientist discovered, like they give their own name to it. But yeah, very good observation. So a lot of them are named after like people and places, like really ancient elements, like stuff that people knew right from 1500s, 1600s, like oxygen, sodium, and all. They have like true names, like depending on whether they came from the sea, like basically Latin, Greek kind of names. But the more recent ones, as people started discovering, they started giving it to honor people and places. So people, scientists like Röntgen, who discovered X-rays, Copernicus, even gods like thorium is named after Thor. Uh, and places like they honor their continent, their country, like germanium is clearly Germany. You have californium, americium, like all of these things, right? Now, what if two different research laboratories, like one in the US, one in Russia, come across an element independently, and both of them, like the US is like, we want to name it, I don't know, New York Cityum, and Russia is like, we want to name it Russium. What do you do then? So,
Make that a Latin name.
so if people are not able to decide what to name it, or to prevent these kind of confusion or conflicts that may come up, IUPAC has decided that, look, if you found out a new element, here's a rule, you name it as per this rule. So the rule is simply, depending on what the atomic number is, if it's a new element, atomic number is clearly going to be in 3 digits, greater than 100. So each digit, like each number, it can range from 0 to 9, right? So depending on what number it is, IUPAC has given like a name for that number, and then it's just like mash those words together. So you have 0 is basically nil. These are coming from Latin again, these words. 1 is un, 2 is bi, like bicycle, 3 is tri, 4 is quad, like quadrilateral, 5 is pent, 6 is hex, 7 is sept, 8 is oct, and 9 is n. Okay. Now, if you had an element with atomic number, let's say 120, what is its name going to be? You just take,
Unbinyl or something like that.
yes,
Unbenilium.
yes. So 1 is un, so it's gonna start with un. 2 is bi, so unbi, and then 0 is nil, nil, and suffix ium. So unbinilium.
Ma'am, why do we add IUM in the end?
Um, that's again like
Is it like one of those rules given by IUPAC?
IUPAC gave the rule, yes, but the inspiration is clearly from the pattern that element names seem to follow, like sodium, chromium. So the etymology of why you like, where did you get IUM from? I haven't researched that. I'm sure it has something to do with like metals or something that forms cations as such. But after that, every single element, people like IUPs use like, yeah, elements usually end with IUM. So it's just to clarify that, yeah, this is the name of an element. That way.
What if it turns out they just added it so that it looks cool?
Could be, who knows.
Ma'am, so as you said, sodium.
Hmm.
How is sodium coming up?
So
I
that
mean,
name was given by ancient people like 1600s, 1700s. So, like again, just like, people had local languages, ancient Greeks, ancient Latin. Sodium, obviously, it's a salt that you get from the sea, like sodium chloride. I mean, all of these Latin names, Greek names originate from either where you get it from or what you use it for. And if you have multiple salts made from the same kind of element, like people were smart enough to figure that out. Like people, those who made the salts themselves or isolated it, like they could figure out that, you take caustic soda, which is sodium hydroxide, and you can make sodium chloride out of it. So, or baking soda or washing soda out of it by making it react with carbon dioxide level by blowing on it or something. And they call it, caustic soda will give you washing soda because this is a salt that hurts you. It's caustic, call it caustic soda. And this is a salt that you use in washing. That's why you call it like washing soda. So it's very generic if you look at the etymology of it. Similarly, calcium salts all have something to do with lime, like slaked lime, limestone, lime water, caustic lime, things like that. So when it came to the element, like, okay, what is this soda salt made from? I guess they said, okay, it is sodium. I'll have to look at the etymology, but I think, what EM stands for is just name of the element. Something like that.
Ma'am,
Yeah.
all this unvinilium, all of that,
Mhm.
that is given by IUPAC, but like there is a different name for all of these elements, right?
Yeah. So this is more of a placeholder name. Like until the world, like everybody agrees on, oh, we are going to name this particular element, this particular name. This is going to be a placeholder name. But yeah, so that's also like a formal process so that there is no confusion and everybody is in the know about it.
But then after that, they'll give it like proper name, right?
Yes. No, that other
I
name
think
is like a formal,
that's how they already have a lot of names of elements which haven't been discovered yet, right?
which haven't been discovered. Yeah, maybe they have a repository of it. Haven't gone so deep into it. Yeah. But yes, so like they give this name so that it's a placeholder name until um, so obviously, like when discovery happens, what happens in the scientific community is they publish papers. So papers, they have a specific format where they give you, like they write the abstract of what the paper is going to be about. They give you the method that they use to test the hypothesis and the reasons why their methods are correct and scientific, and the logic behind why it holds up. Like all of these details are given. And it's not just randomly publishing, people just don't randomly accept it. There's something called a peer review process that happens. So other people read the paper, they may replicate the experiment, and then they'll be like, yeah, this paper is correct. Whatever those guys have done, they've done it absolutely correct. Their logic is correct. And this is a good finding. So all of this process happens. So like even if a new element or a new compound were discovered, something new is discovered, it is first published in scientific journals, other people verify it, and once it has like a stamp of approval of sorts in the general scientific community, then announcements are made and things are formalized. Like that's kind of how the process happens. Okay. Hmm?
But is it possible? So, for example, for the modern periodic table, let's take sodium. Could there be an element even before sodium, but we haven't discovered it? Could it be possible? And if it is discovered later, would it be kept before sodium or after 118?
So one, they've been like, oh, it's 2021 now, right? So all of this atomic number was all of this research happened in 1900s. So almost been more than 100 years since the um, what do you call it, since atomic numbers have been assigned. And then there have been more experiments based on it, like people were finding out spectra, people were figuring out structure of atom, all of that was happening. So it has been established as correct, like whatever atomic numbers have been like that you are studying about, these are all established, verified, nothing has come up till now. So we can be sure that they're all correct, and there won't be anything between atomic number 18 and atomic number 19, or sodium is 11, right, between atomic number 10 and atomic number 11. If something like that has been discovered, either it is wrong, or our whole understanding of atomic structure and how the nucleus exists, the number of protons, like our whole understanding of all of that would be proved to be wrong. So
Like earlier, Mendeleev left spaces because he saw a significant gap in atomic masses, but that won't be possible for atomic number because you can't have like 18 point something
exactly,
as
correct. So if at all it happens that if somebody finds some 18.5 something, then either that person is wrong, their finding is wrong, or it means that whatever work has been done over the past 100 years was all wrong. So yeah, that's like an impossible situation. Yeah. But coming back to this chapter, you guys, like this is the main thing that you need to study about. Naming of elements, like whatever based on IUPAC rules, like giving them the placeholder name based on the atomic number. Okay. Have you guys noted down this table in your books?
1 second, ma'am.
So note it down, and then we'll practice some. Like I'll give you guys 3-4 names that you can practice with, and then we'll get down to studying about electronic configuration and groups and periods and all that.
is this table in the textbook also?
Yeah, it is, but I would suggest write it down because writing it will help stick in the memory.
Ma'am, is this before the periodic table? Since our class did not do this, like naming of them.
Oh, this is part of the chapter. This wouldn't be
But
So will
I
we
don't.
have like questions on naming elements?
There is a small chance. That's why we're just gonna practice 2 or 3. But this is not very complicated. You literally have to put 3 of these words together and then add em at the end. So, and most of the words you can instinctively remember, right? Like 2 is bike. You have bicycle, bipeds, like 2 legs, right? 3 is try, like triangle, quad, pent, hex. All of these are common things that you already know of. 7 is sept. Okay, 8 is oct. Also, you can do it. You just need to learn 0, 1, and 9. Just be familiar with that.
It's pronounced as N.
N, E double N.
And after everything, Liam is compulsory.
Liam, nai, just IUM.
IUM, yeah, so that's compulsory.
Ma'am, and there's like the table of this entire EM and all of that of the till the 118th element. So do we have to remember the names and all that?
You don't have to remember it. If you remember these 10 words, you can.
No, not this. The official name.
Oh, I don't think so. No. No, you won't be asked to remember the official.
Ma'am,
Hmm?
I have a question. So if we followed this table, will hydrogen be like unium?
Yeah, technically, yeah. Imagine helium. Bi-IEM. Bi-EM. It's got 2 I's there.
Ma'am, so this rule starts to apply from after which element?
After synthetic one, so after 100.
Is the 100 included in that, or does it start from 101?
101. Like usually it is applicable, like the kind of questions you'll be asked is like 107, 108, or 118 and things like that. Oh, another thing. So this is the name. What would be the symbol? Like how do you find out the symbol from this name?
The first letter of each.
Absolutely.
120 it will be U B N.
Yes. And just like with other elements, the first letter is capitalized and the other elements should be small.
Ma'am, I didn't understand why we added N.
Plus 120, un by nil.
Oh, okay. Yeah, I understood.
And the symbols based on the official name are those are different.
Yeah, they're completely different. They follow random logic, like the first 2 consonants. I mean, getting symbols for those, you also have to look at, is there an element existing with LI or something like that? Then you take the next alphabet. It's like that. A little more complicated. It's not, doesn't follow a pattern.
Also, ma'am, I have like a silly doubt. Is there a reason why sodium symbol is Na? Like, how is that related?
Yeah. So sodium is the Greek word, like soda comes from, I think, Greek. The same element in Latin was called natrium. So the Na comes from the Latin name.
Yeah, a lot of the element names, like which don't match up with the symbol, they come from a Latin name. Same with, I think, phosphorus, right?
No, phosphorus is P.
Potassium, sorry, potassium.
Potassium,
I
yes.
keep getting confused between them. Potassium, then gold, silver.
Yeah. Mercury. Iron. Iron is like IRON.
Yeah,
The Latin name is ferrum or what? Yeah, ferrum. Yeah, and that's why its ions name are also called like ferrous and ferric, not
yeah.
so something like
Ironic.
that. Yeah. It's funny. Hmm. The potassium is called kalium. That's why it's K. Hmm. Okay. All right, you guys done?
Yes.
Yes, ma'am.
Hmm. Just give like 3, 4, not a lot. 105. So give the name and also the symbol.
You
Unit.
have to like write it in the chat.
Yeah, yeah, write it in the chat. That way you're not like talking over one another. All of you have a chance to answer. Yeah, Kaveri got your answer. Hmm. Sanat, correct. Rishit, you're like 95% correct. So one is not uni, it's just un. Yeah. And also you need to send the symbol. Kaveri, yes, second one is correct. Got it. And she's got the third one also. Awesome. Yes, Sanat, second is correct. So this is un, nil, pent, and em. Rishit, yes, second is correct. Sanat got your third. Absolutely right. So Rishit, the last one is remaining for you. Symbol is
So, ma'am, like all of the ones you made us do right now, at some point these were actually named these names.
in fact, if you look at
So,
publications from I don't know 5, 6 years ago, like when I was your age, these were the words I would see in the periodic table, like on Wiki or anywhere else. Yeah. So yeah, if you go back 10 years, 12 years, if you look at those publications, those books, these are the ones you'd see there.
So
so
these
basically,
elements.
whatever we made out of our imagination is like was something real at a time.
This is, I mean, these are, you're just following rules. It's basically like math. IUPAC
Wow.
set the rules, you're following that.
These
But like
elements.
these names don't exist anymore, right?
No, not anymore. Kaveri, you were saying these names?
These elements must be really young, right? Like it must be recently discovered. If 10 years ago we used to use this IUPAC nomenclature.
Yeah. Yeah. These were discovered like very, very recently. When I was like in seventh, eighth standard, I had studied it as, oh, there are 108 known elements. And now when you guys, now you guys are born and now you're studying, and then you're studying about 118 known elements. So 10 of them were created in the last 10 years.
Ma'am, so if an element is 717, so the symbol would be sus, right?
717, wow. That's yeah, it's us. That would be the element of Among Us. Hmm. Okay, now coming back to this, we're gonna start studying about the periodic table. So again, You guys tell me if there's any specific part of the chapter you want me to focus on, or do you want me to do the whole thing in detail?
Uh, so this chapter is over, or what did you? Can you just repeat it?
Yeah, it's not over. We'll be studying about the periodic table now. So two parts to it. One is we'll be studying each block. Like first we'll study about electronic configuration. So it's going to be again, if I point out any element based on its place in the periodic table, you guys should be able to figure out the electronic configuration. And the other way around, like if I tell you the electronic configuration, then you need to figure out which group, which period you will find it in. Second part is just studying about the properties of the periodic table, like each block as a whole, we'll talk about the general properties, and each property will study about the trends across a period and talk to down in a group. So out of this, like I want to check with you guys, like if you guys think it's pretty easy, if it's something that you can do, I'll just take it as a Q&A format. But if there's any particular part that you want to go deep in, we'll do that. Or do you want to, do everything in detail?
I mean, for me it's easy. So basic teaching is fine, I guess.
Okay, like a Q&A kind of a thing.
Yeah, and maybe the major topics. So like electron enthalpy or ionizing enthalpy and those all topics.
Kaveri and
And ma'am, can I, okay, after you ask them, can I just ask my electronic configuration doubt after that?
yeah.
So since I had it.
So Sanat and Kaveri, what about you guys? How do you wanna go ahead in this chapter?
I'm fine with anything really because in school we're like done with the entire thing. So I pretty much understand everything, just have to go over it again so that it's fresh.
Okay. And Kaveri?
The trends part, if like in detail, would be good. The
Okay.
blocks and all. Fine.
Okay. All right. So the first part of it, I'll just like breeze through it. Um, let's see
Ma'am,
how confident you guys are. Okay.
I
So
have a question.
yeah,
So, like, since the Rajan student aren't here, will you be repeating the same thing with them?
yeah. So basically, when you guys have your exams, like when you do your mock test
Oh,
and
so it's like rotations.
for a little bit, yes. Once you're done with your exam, again, all of you will be together again.
Ma'am, so my question was,
Hmm.
so for example, let's take the rhodium only, or whatever it was called.
Hmm.
So in that, so as you said, I remember where the electrons go to the lower level first, the lower level energy part first. So basically, first all the s orbitals will be filled. Like how many ever shells are there? So from 1s to 5s. So first all s will be filled, then p, and then d. Or should we like
Rishit, you need to revise structure of atom.
all? Ma'am, I know that, but then you said that first it will go to s and then d. So I know that Thor's law or whatever it was, the
Oh,
energy.
principle, and you have Moore's law, like helping
Yeah, correct. Yeah, that one I remember. But then again, right now you said like it would first go to 5s and then it will
yeah,
come to 4d.
specifically 5s के बाद 4d आएगा. Does not mean all s will be filled first. So this is the order, right? 1s and then 2s and then 1s 2s 2s तक यहाँ पे हो गया. After 2s 2p is filled up. Then you go to 3s 3s1 3s2. Then 3p is filled up. So 3p1 से लेके 3p6 तक. Then it's 4s 4s1 4s2 के बाद then 3d is filled up. Then 3d 10 तक खत्म हो गया. Then 4p starts getting filling up. Then 4p1 से लेके 2 3 4 5 4p6 4p6 fill करने के बाद 5s is filled. 5s के बाद 4d is filled. So 4d 1 से लेके 4d 10 तक. So once the 4d orbital is filled, then you fill 5p. So this is the order of the electronic configuration that is filled. And incidentally, I also showed you how it is easy to figure out the electronic configuration. So you don't have to remember of Gauss principle, Moore's law. Just by looking at the like place in the periodic table, you can figure out the electronic configuration. So what I mean is, if you take, for example, phosphorus, the place is over here. How do you reach phosphorus? So if you want to find out the electronic configuration, two ways to do it. One is the expanded form, like where you start from 1s, 2s, and so on. And then you have the contracted form. Contracted form, matlab, you don't have to write the whole thing. So first thing is, which is the first noble gas before phosphorus?
Neon.
Neon. Neon is the closest one. So write neon in square brackets. What this represents is neon tak electronic configuration aega. And then after neon, you have phosphorus, right? Which period is phosphorus in?
Third.
Third period. And which group is it in? Or rather, which
15.
block is it in? Like, think of which block it is.
P.
P block, right? Which means that phosphorus ka last thing is 3p. So just check, neon yahan pe hai. How do you get to phosphorus after neon? So pehle you go through these two elements, which are third period ke S block elements. So uske baad you have
3s2.
2. And when you reach P block, 1, 2, third element is phosphorus. So 3s2 ke baad it is 3p3. Okay.
The number of is dependent on the number of elements we pass.
Yeah, basically. Another one, like let's say selenium. So can you guys try for selenium?
Ma'am, do you want like the expanded form or the contracted one?
Let's practice with contracted first, like just get to the last one. Expanded is again the same logic, but you do it right from the beginning. So
Ma'am, I have a question.
Hmm.
So like for selenium, do we have to write the D block wala also?
Yes, because you have to pass through the D block to get to this P, right?
So we'll have 3 orbital types, right?
Yeah.
Okay.
When we take a noble gas, we take the gas which is before the element, right?
Yes. So in this case, for selenium, what should I take? Should I take argon, krypton, neon?
Argon.
Argon. Argon के बाद
4s2.
4s2. Then cross किया
4d10.
3d10, no?
3d होगा. So with D block, you're filling the 3d orbital after 4s, right? So this also another way to look at it is, this is the first row in D block, right? इसके पहले और कुछ नहीं है. And which is the first d orbital you come across, like 1d, 2d, 3d उसमें?
3D.
3d is the first one. So first d row is 3d. So 4s2, 3d10. Then, okay, we've crossed the 3d part of it.
So now
Then
what
again 4.
4 or 3?
4.
This will be
4p4 ना it'll be.
तो 4p में है अभी हम, like fourth period p block, उसमें fourth element is selenium. So 3d10 के बाद you have 4p4.
So we just go with the
Ma'am, okay, Kaveri, go on.
energy level.
Yeah, I mean, that's what it is. Yeah, that's exactly how you do it.
So, ma'am, if we have like any element in the F block, do we have to write like first S, then D, then P, then F? Sorry, S, P, D, then F.
You haven't reached P yet, so it's first S, then D, then F.
Oh, okay, yeah.
D1 होगा, something like that. D also nahi, like okay, like in some cases it jumps to 5D, in some cases it won't, but yeah. Again,
Ma'am,
higher elements are weird. So yeah.
if we're looking for an element, say like 73, like for
Mhm.
example, so uske pehle there is like lactanoids, right?
Yeah.
So what would be for that?
So 57 के बाद 72 आ रहा है, which means that after this, like okay, so xenon. So if I'm doing it for TA, I don't know what it is. TA के पहले you have xenon. So xenon का noble gas configuration. Then you're getting through the two S elements. Which one is it? So 1, 2, 3, 4, 5, 6. So 6s2. Then you're getting through the 14F elements. 4F14. 14F elements के बाद you're reaching this D block. So then it will be 3D, 4D, 5D3.
What are the maximum number of electrons in F?
You tell me.
14.
F orbitals. F orbitals is like the L value is 3, 0, 1, 2, 3, SPDF. 3 matlab the M values range from -3 to +3. So that's a total of 14. I mean, that's a total of 7 orbitals. Into 2 will take 14 electrons.
Why into 2?
How many electrons will you find in each orbital?
Two.
Yeah.
Ma'am,
Hmm?
now if you're doing it in expanded form, then how would we know?
But like you start right from the beginning. Acha, before we do expanded form, have you guys done this in school, like practiced electronic configurations? Like, do you have questions based on this? Any question, ma'am?
Yes, ma'am, we did.
Okay, so is your teacher insisting on writing the whole electronic configuration, or is this okay?
I don't
I mean,
remember.
whenever there is a question of electronic configuration, but it's specifically that question, then I mean, it's for the electronic configuration, then yeah, then ma'am says for the expanded form, but ma'am never said like write contracted, so I don't know.
Okay.
But
The
I-
reason
uh,
I
any and
yeah, so the reason
anytime, oh sorry, yeah. So basically, I'm saying anytime there was a question of electronic configuration, that was the question asking itself. There was nothing like the question did not ask, but we had to write it. But whenever we did, we wrote the expanded form.
okay, then write the expanded form only. The reason I asked is like for practical purposes, if you just do a Google search, the contracted form is what is always used. So I wasn't sure if your teacher accepted this or if you had to write the whole thing. That's why I checked. Okay. So expanded form ke liye, again, let's take the same thing. If I go with phosphorus, you start right from the beginning. So first you have to go with one S block. So 1s2. 1s2 helium technically should be over here, but because helium ka orbital is filled and it's a noble gas, it's placed over here. So 1s2 ke baad you go with the 2s elements. So you have 2s2. 2s ke baad what do you go through?
3s, I mean 2p.
What into helium?
One moment, Kaveri. Let's finish this first. So 2s 2p khatam hone ke baad what do you go through?
3s, 3p, 3d.
Oh, itna lamba nahi. You're trying to reach phosphorus. So you go through 3s and then the third element is phosphorus. So 3p3. The logic is same, just that you go like right from the beginning. If you remember noble gas configurations, that neon is 10, so it will basically be like 1s2, 2s2, 2p6, then you can write it automatically. But otherwise, if that is something that you don't remember, then this is how you like go with it.
Can you take one element from the D block?
Yeah. Do ion. You guys do it. I'm not gonna say anything. I'm gonna be quiet.
Expanded or contracted?
Expanded.
First few will be the same as phosphorus only. 1s2, 2s2, 2p6. Then 3s2.
Yeah.
Then 4d.
No. 3s2 you've reached over here. यहाँ से यहाँ you jump.
3p6.
Yeah.
Then 4s2.
Yeah.
Then 4d.
3D10.
3D
Sorry, no, 3D5, 3D5.
5.
3d6.
Wait. Oh yeah, I didn't count it properly.
Yeah. So Kaveri,
So
don't get confused.
start with 3d, right?
So one hack is whenever your like S and P are always the same. Like if you start with 2S, you'll be in 2P. If you start with 5S, you'll be in 5P. D and F के लिए it goes down by 1. So 4S2 हुआ, so you go with 3D. 5S2 हुआ, so you go with 4D. And then for F, it goes one less. So 6S, then 5
5d.
and 4F. Yeah. So only
Okay.
for D left.
Again, one more round.
Yeah. With D, it's -1. F, it's D say -1. So basically S and P ka -2. And S and
S and P always remain the same, like according to the period.
yes. Yeah. Let's do it the other way around. If I give you guys an electronic configuration that's, let's say, just gonna Google search one thing. Point it out. Okay, so this is your electronic configuration. It's XC 4F14 and 5T10. So
it's after xenon.
it's after xenon, yes. This is incomplete. Wait, I'll tell you. 5D10, then 6s2 and 6p4. So your valence electron is going into, like it is the 6p4th electron. So what you need to give me is just which group it is, the number, and which period you find it in, the number.
Ma'am,
Yeah.
after whatever noble gas it is, it has to be S, right? How do we like go directly to F?
See,
Because after noble gas, we will go to the first two groups.
so there are two ways of writing it. One way of writing it is in the order of how it gets filled up. Another way of representing that you would find in like general this thing is the what do you call it?
principal quantum number.
Chronological, yeah, it's like numerical order, not alphabetical. It's numerical order. So all the one SPDF, two SPDF, then three SPDF, then four SPDF. So that's another way of representation that you get.
Excuse me, ma'am.
But that does not matter. Like just by looking at 6P4, you can figure out which group and which period. Sanat, yes, you have gotten it. Can you tell me what element it is? Send it on chat.
Oh, okay.
Ma'am,
Yeah.
now I think 5D is the last one, right? So it would fall under fifth period, right? And then for the group, do we need to go?
So it filled up 6p tak ja raha hai. So 6p4 is the valence electron.
Then I'm sixth period, and then from P fourth element, right?
Yes. That's
So it's LV.
count properly. But you have to like you're very close, Rishabh.
Ma'am,
Yeah.
how will 6p be the last one?
See, the order of filling is Hamesha pehla, like first thing to be filled is S. S ke baad you get your D and F, depending on which element it is. D and F ke baad the P is filled up, right? If I did not give the 6P4, then you need to figure out, okay, 4F14 or uske baad 5D10 is the last one that's filled. But then
So it's
I meant 6P4. So that will be the last test one.
But then what will happen to F?
You're crossing F and then coming to the P block.
So it's first 6s2, then 5d10, and then F, and then P.
The other way, 6S ke baad F, then you
4f, then 5d, and then 6p.
Ma'am, how is that 4F14?
you're filling up the 14, like the F part.
No, like 4. How is it 4?
I told you, right? Like D is always -1 and F is like -2. It is the
Oh,
first
okay.
F orbital that's filled, and the first F orbital is 4F. So that's the one that's filled. Ah, Kaveri also got it. Located the element, she found it. So Rishit, just waiting for you.
Is it not LV? It's not that.
Really close. You just have to, like, you haven't counted properly. So, sixth period, right? So, this is the first period. This is second. This is third. This is four. This is five. And this is six. LV is in the seventh period.
Oh, 8T. Okay.
Yeah. So, the element that I searched out was polonium, which is over here.
So, ma'am, we have to we don't have to really pay attention to the ones before. If like whatever is the last one, that's the only thing we need to look at.
Yeah. So the one thing you need to remember is what is the order of it. Like this, I just picked it out of internet, and this was the format it is given in, right? So you needed to ensure, like, make sense of it. That yeah, you shouldn't look at F, you shouldn't look at D. P is the one you need to look at. So the only thing you need to know is remember the order. Hamesha S, then agar F hai to F is filled, then D, and then P. So
So
based
if we have 64, we would have picked 5d10.
sorry, what? Can you repeat that?
If we didn't have 64, you were taken 5d ka whatever. 5d.
Correct. Yeah. So even though it was given in this format, then 6S is filled first, uske baad F and then D. So D 5D10 is where you need to stop and look.
Can this be after Standard form.
I didn't get you. Standard form in the sense?
Expanded.
Expanded. Okay. Expanded तो बहुत लंबा हो जाएगा. So expanded हुआ तो you won't get like D and F wala elements. Maybe they'll give you things like arsenic, selenium, like strontium, stuff like that. But you won't get like all of this.
Ma'am, if it's an element beyond the first 20, will they give the atomic number and all?
They may. You can still easily calculate the atomic number. Just add up all the number of electrons and you'll get your atomic number.
Will we get to use the periodic table?
Maybe you'll get application based questions on it. So if you're able to intuitively understand the periodic table, take advantage of the way it's divided it into blocks and the groups and the periods, then whatever kind of questions you get, you'll be able to work on it.
But like if we have to identify an element based on the condensed form or whatever, we have to like the periodic.
Like if you're given those kind of questions, they also have to let you use the periodic table or give an excerpt or something or the other. So you should be given the resource. Nobody expects you to remember the whole periodic table. No, don't remember like every single element on it. Otherwise, that defeats the purpose of the existence of the periodic table. Okay, so that's like how you figure out, like that's how you relate the electronic configuration to the position in the periodic table. Like they both are, this is the shape of the periodic table. It is created in this way to help you with different aspects of it. And that's how you take advantage of the electronic configuration. That's one part of it. Okay. Then, yeah. So again, as you guys said, each period represents a new shell. So every successive period means that a new shell is added onto the element. So that's a new value of n, principal quantum number. Then,
Ma'am,
yeah.
so like you said for F we go 2 down, like so it was like 6, it'll go to 4F.
Huh.
If it's 7, then we have to know that it's going to the next period, right?
Yeah.
Beyond that,
That is correct. Beyond that, again, elements are not discovered, so there's no new row. If at all there happens to be an element, you'll get a new row. And yeah, like the position, basically the group number represents, where exactly the last electron has gone. That's that. Then, yeah, and then come to the blocks SPDF. So let's quickly go over the properties of S, each block, starting with S orbital, highlighted S orbital. Helium is included in the S orbital, yet it is placed over here. Why?
Because it, like even though it has the same number of electrons as the s orbital, but it has a complete shell because it's the first shell.
Correct.
So it displays properties similar to noble gases.
That is correct. So if you strictly follow the electronic configuration, helium is 1s2, which means that it should be here with the s block. But again, it's the first shell. S can have only 2 electrons, which means fully filled orbitals. So it is more fitting with the other noble gases because those are the properties that it shows. That's like one anomaly of helium, like position of helium, that is an anomaly. Similarly, we'll also come across, anomaly with hydrogen. Sure, electronic configuration says 1s1, but it kind of shows similar properties as halogens, where it forms covalent compounds and it's a non-metal and it's gay, like it exists as a gas. So yeah, that's another anomalous position.
strictly going by electronic configuration, it should be placed with after hydrogen, right after hydrogen.
Yeah.
But then matches with the the properties of noble gas, we place it in the 18th.
Correct. Yes. Okay. Now coming to the properties of the S block. First property we have is, yeah, what is common in S block? Like, how do you define S block? Why are these elements placed in S block?
Electronic configuration.
That is correct. So it relates to electronic configuration. So what is the general electronic configuration that these guys have?
NS2.
Correct. Not just NS2. So they have NS1 or 2. So if it is in group 1, they all have NS1. If it is in group 2, they have NS2. Yeah. So this is like the general electronic configuration. The last electron enters the S subshell. That's why they're placed in the S block. And other common properties. What kind of elements do you find in this block? What is common amongst lithium, sodium, potassium, magnesium?
Also, I guess they can give away electrons,
Yes, they are
so
electropositive.
that is why metallic. Yeah.
Correct.
High metallic character.
Yes, they are all metals. Any speciality about the metals? Because you find metals in D block also, and to some extent in P block also.
Alkali and alkaline earth metals.
That is the formal name given to them. But what is special about alkali and alkaline earth metals? How are they different from,
Form cations.
what was that again?
They form cations.
Electropositive matlab cations, they give away electrons easily. So do these metals like copper, iron. But how do sodium, potassium, these metals differ
I
from?
think they can give away electrons much more easier than them.
That is correct. Or in a single word, they are
Electropositive.
electropositive is like giving away electrons easily. But if a metal gives it more easily than others, these metals have a tendency to just give it away just like that. What does that make them?
Highly reactive.
Absolutely. That was what I was looking for. So this block consists of metals that are extremely highly reactive. Another common property is that they're all like soft metals. You guys remember, you can cut sodium, potassium with a knife, with a butter knife. You guys remember that?
Yes, ma'am.
Even like magnesium ribbons. You guys have had lab practicals, right? Like it was pre-pandemic. So you guys get to see.
Yeah, the magnesium ribbon we did.
Yeah. So that also you can like bend quite easily. So S block metals are characterized.
And also sodium, we could just cut it with a knife.
Yes. So S block metals are characterized by their high reactivity, and they're all like really soft metals. What else can you say about them? And they've got low boiling points and melting points. Okay. So metals you find in a lot of places in the periodic table, but what is special about S block metals is that they're highly reactive, they're soft, and they've got like low boiling points and melting points. Like cesium, I don't know if you guys remember that video, but you hold it in the hand and then it starts melting. Really low melting point.
Gallium and cesium.
Yeah. What else? Electropositive and metallic. Yes, we covered that point. And yeah, because they can give electrons really easily, they are strong reducing agents. Yes, know what is the meaning of like oxidation reduction?
Yes, ma'am.
Everybody,
Reducing means they lose oxygen and gain hydrogen easily.
that is correct. What is reduction in terms of electrons?
Reduction is gain of electrons.
Correct. So
And
reduction is
oxidation is like the opposite.
absolutely. So reduction process is gain of electrons, which means that if I am gaining electron, I need to get it from somewhere, right? So what I get it from is reducing agent. Now, because these elements can give electrons easily, they form strong reducing agents. Okay. So these are properties of S block. So what you can do is, if you're taking down notes, you can like make a table of it, like S block, P block, D block, F block, because all the properties that we'll be talking about will be on the same lines. We'll discuss their electronic configuration. We discuss like the general properties of the elements that you find in there. Okay. So
If they are strong reducing agents, so they have to combine with some other element, right? So
yes,
they cannot, so they won't be found. Can they be found like just individually?
no, never. Not in natural state. You have to process them to get pure metals. Never naturally. You won't find them pure.
Ma'am, I could be wrong, but strong reducing agent does not does it mean like they gain electron, right?
No, you are wrong, Rishab. So reduction is gain of electron. Okay. So for example, let's take this equation. Na plus Cl gives NaCl. This is a redox reaction. What is getting oxidized and what is getting reduced in this?
If it's Cl minus, I'm pretty sure that is getting reduced because that's gain of electron
That
and
is,
Na is oxidized.
yeah. So Cl2 is gaining electron because it was neutral first, elemental form. फिर यहाँ पे -1 हुआ. So it gained an electron. So this is reduced. So this process of Cl2 becoming Cl minus is reduction because gain of electrons हुआ. Now where did chlorine gain this electron from? Extra electron कहाँ से आया?
And
Sodium.
Sodium. Now because sodium can lose electrons easily, that sodium was the source of electron for chlorine, right? So this gave out electron easily. That is why chlorine could take this, right? So which means that because sodium was present, chlorine was able to get reduced. So sodium is the reducing agent and chlorine is the one that got reduced. Make sense?
yeah, I had this kind of doubt from last year itself. So yeah, I'm not surprised I got it wrong.
Source, like imagine like travel agent the one that travels with you?
I mean, that depends on the agency. They do provide a guide.
Guide is different. Agency like travel agent is there only to give you the tickets and give you the hotel and all of that. Yeah. So yeah, agent is because it is enabling, it's doing something, and reduction oxidation happens to whatever other thing. That's kind of it. The source of the electron is sodium, isliye this is reducing agent, and this is the one that got reduced. Okay. All right, so these are like the properties of S block elements. So similarly, let's quickly discuss it for P block elements. Have you guys noted this down? Can I clear this?
Yes, ma'am.
All of you?
I haven't noted it down. Can I do it after class? I'll just check the recording and note it down.
Okay. I would like, if you want, you can go through like the chapter notes or your textbook and work it out also. And in case you're stuck somewhere, you can watch the recording. That way, you'll be able to process it in your head, like you'll be literally studying. Okay.
Ma'am,
Yeah.
what are the general criteria we are categorizing it in the SPDF? The general notation and the electronic configuration, if they are electropositive and all that.
Yeah.
What else?
What is of the elements basically? What kind of elements do you find? Just general properties. Okay. So next, P block. General, what is the electronic configuration? Where does the last electron go in P block elements?
From NP1 to NP6 anyway.
Correct. So it's usually like noble gas configuration, and then they have fully filled NS2 and then NP126. So this is the general electronic configuration. Point number one. Next, what kind of elements do you find? Metals, non-metals, metalloids? What sort of elements do you find here?
I feel this is completely non-metal, right?
Is it completely non-metal? Is aluminium a non-metal?
Okay, maybe
It's a
just
mixture.
a bit. Yeah.
So P block is the most diverse of all the blocks. You find metals, non-metals, and metalloids, all three types of elements here. S block was exclusively metals, with the exception of hydrogen. But then one could argue that that kind of shows metallic properties to some extent. But yeah. D block is also exclusively metals. We'll come to that when we discuss it. F block is also exclusively metals. All these three blocks, all of them lose electrons. P block is the only block that has metals, non-metals, and metalloids, all three types of elements in them. Okay. You also find, okay, these kind of elements are also characterized by something like high electron gain enthalpy. Definitely more than your SP or S, D, and F blocks anyway. So these elements usually have high electron gain enthalpy. They can gain electron easily. And that means if they can gain electron easily, what would you say about, are they oxidizing or are they reducing?
Oxidizing agents.
Yes. All these elements form good oxidizing agents.
Gaining electrons is oxidation, losing electrons reduction.
No. Oil rig. Remember oil rig, Kaveri. Oxidation is losing electrons and reduction is gaining electrons. But when we talk about agents, if reduction is happening, it needs to get electrons from somewhere, right? So that would be reducing agent. If something is losing electrons in oxidation, something else must take those electrons. Like electrons just can't swim around randomly, no? So the elements that take the electrons form good oxidizing agents.
So in oxidation, it means losing electrons.
Yes.
But the one that oxidizes, that is the oxidizing agent that has to gain the electron.
Correct. So that itself undergoes reduction. And because it itself is getting reduced, that means that something else should be oxidized. So it is an oxidizing agent for that other thing.
On the opposite.
Yeah.
Ma'am, if we also consider metals, shouldn't that also we should also consider that they can also give electrons?
Yeah, absolutely. Like it's
So
not
we cannot.
right. If you compare sodium with aluminium, sodium is a better oxidizing, reducing agent than aluminium. And aluminium is a good better oxidizing agent than sodium. But if you compare aluminium and chlorine, then clearly chlorine would be a good, better oxidizing agent than aluminium. So in general, compared to other blocks, the elements in this block form good oxidizing agent. Of course, again, comes with a caveat that except the noble gases. So noble gases will not do like oxidation or reduction, like they won't take part in any reaction at all.
So the ones on the left are better oxidizing agents, and
Yes.
as we go right, it's
Left, no, like ones on the right are good oxidizing agents because they can gain electrons easily. They can form anions better. And the ones on the left are good reducing agents. So here they are reducing agents. And
oh yes, I'm getting really confused with the oxidation reduction.
don't worry too much about oxidation reduction. We have a whole chapter on it coming up later on, redox reactions ke bare mein. So yeah, we'll do all of this again. Just remember the basic oil ring and remember the difference between reduction itself and reducing agent, or oxidation itself versus oxidizing agent. So this is about P block. You have metals, non-metals, metalloids, high electron gain enthalpy. They also have high ionization enthalpy because it's difficult to take an electron out. And yeah, the oxidizing character increases on this side. So this side they're all
So the high electron gain enthalpy is first that they can also gain electron, and that is what it is, right? And it is also related to the an amount of energy released or something like that, if I'm not wrong.
it is defined as the amount of energy released when electron is added.
So when they take in high energy is released, right?
Correct. Yeah. So I'll go into detail when we discuss all of those properties and when we're doing the trends. Yeah.
So high electron gain enthalpy is not for the entire block, right?
Like obviously the entire block won't have the same value of electron gain enthalpy. Again, these are the properties we are talking about as opposed to other blocks. Like we are comparing each block and then talking about them, right? So we said were really good reducing agents. We're saying that the elements in P block are characterized by high electron gain enthalpy. So usually these elements that are there on the extreme right, they tend to have high electron gain enthalpy than the ones on the in the other blocks.
The ones on the extreme right, they are good oxidizing agents, right?
Not noble gases, but yeah, like group 6. Yeah.
So if they are good oxidizing agents, it means that they gain electrons, correct?
Yes.
If they gain electrons, then they have high electron enthalpy. Okay.
Yeah, they like gaining electrons. They don't mind being negative charge. Yeah. Okay. And then we'll talk about D and F blocks. It's 5:30 already, so we'll continue this in the next class. How long before you guys